So in the previous video lecture, we discussed and arrived at a few equations that connected several parameters that are of significance when a charged particle moves through a magnetic field. So some of them, just for recollection, were R, which is where R is the radius of the circular motion that's been executed by a charged particle as it moves through a magnetic field of strength B with a velocity v having a mass m and a charge q. So R is equal to mv by qb. Similarly, we also said the angular speed of such a particle, the angular speed being shown by the particle, can be arrived at by the relationship omega equals qb by m. And finally, we also discussed how when a particle executes helical motion while moving through a magnetic field, you can also arrive at the pitch of the particle by using the relationship P is equal to 2 pi m into the parallel component of, we also talked about the pitch. So pitch of the helical motion that's being executed by the charged particle, and we said pitch is equal to 2 pi into mass into the normal component of the velocity being exhibited by the particle divided by the charge and the field strength, the magnetic field strength. So one important natural phenomenon highlights the helical motion theory that we just discussed. So that is the phenomenon of auroras. So auroras are natural phenomena that are observed by people living closer to the North Pole and South Pole. So in the North Pole, typically auroras are called as Aurora Borealis, and in the South Pole, closer to Antarctica, they are referred to as Aurora Australis. So what is an aurora? So an aurora, you can type out aurora on YouTube and you will see beautiful wavy screen-like patterns in the night sky that are a visual spectacle for the people who live in the poles. And these wavy patterns come out in colors like blue and or orange or reddish tinge. So what causes these wavy patterns of fuzzy light called as auroras? So that can be explained by the helical motion that's exhibited by charged particles when they get to move in a magnetic field. So you might be aware that the Earth behaves like one giant magnet. So the Earth behaves like one giant magnet with the north and the south over here. And you have magnetic field lines which connect the north to the south. So by convention we assume that they emerge from north and terminate at the south. So you can see when we visualize this in a 3D image, if I have a globe over here, the lines all spread out from the north and terminate at the south. So whenever now a charged particle which is released by the sun releases millions of charged particles every second, and especially when there's a solar flare that happens in the direction of the Earth, then millions of those particles, they arrive from the sun and get to move through the magnetic field of the Earth. And as they move over here, they get stuck with one of these magnetic lines and they start exhibiting the helical motion towards one of the poles, either to the north or to the south. Now, typically for a person closer to the equator or the Tropic of Cancer or Tropic of Capricorn, in this latitudes, the field lines, the magnetic field lines are further apart. So we don't see these particles collide with each other. They move in their own distinct helical paths. But observe closely, as the lines are coming closer at the poles, these particles, charged particles, they start smashing into each other at the poles, and they also start smashing with the atmospheric atoms, and that's when they produce this beautiful wavy fuzzy light-like phenomenon that we call as auroras. So in North Pole they are called as aurora borealis, and in the South Pole they are referred to as aurora australis. So this phenomenon is completely explained by the phenomenon of a charged particle exhibiting helical motion when traveling in a magnetic field. So now let's shift our discussions to what happens when a charged particle moves in a combined electric and magnetic field. So for simplicity's sake, let's take the electric field and the magnetic field to be perpendicular to each other. So if the electric field is acting in a direction which is upwards, let's say the magnetic field is acting in a direction perpendicular to it, which is from the right to the left, or it could also be from in front of me towards me. So these are the other two directions in which are perpendicular to the direction from bottom to top. So we'll assume that the electric field is acting upwards along the y-axis and the magnetic field is acting along the z-axis. And we'll also assume that both these fields are perpendicular to the direction in which the particle, a charged particle Q, is moving with velocity v. So I'll assume that is happening in the x-axis. So a particle Q of charge Q is moving with velocity v. So what do you think is the force acting on this particular particle? So we know by Lorentz force that we discussed previously that the total force is a combination of the force felt by the charged particle due to the electric field and due to the magnetic field. And we also know that Fe is given by Q into vector E, and the force due to the magnetic field is given by Q into the vector product of the velocity and the magnetic field. Now if I were to convert this into normal multiplication, I would need to replace them with unit vectors with respect to directions. So if I do that, I get Q into E multiplied by the unit vector in the direction of the electric field, which is denoted by the letter J cap, if you recall, plus Q into velocity into the unit vector in the direction of velocity, which is x-axis, given by the unit vector I, multiplied by B into the unit vector in the direction of the magnetic field, which is given by K cap. I further simplify this, it gives me Q E J cap plus Q V B I cap into k cap. I cap into k cap. Now you might realize that I cap into k cap is nothing but minus j cap. So I cap into k cap gives me j cap, but in the opposite direction. So it's minus j. So that gives me q e j cap plus q b b into minus j cap. The reason being I cap into k cap is equal to minus j cap. So this is my combined force that's being felt by the particle. So to further simplify this, I will get F L is equal to Q, which is common, E minus VB into J cap. So this is the combined force being felt by a particle that's traveling perpendicular to both the magnetic and the electric fields, which themselves are perpendicular to each other. So we arrived at the equation for the combined force being felt by a particle. So it is Q into E minus VB into J cap. Now, if you are a keen observer, you would have observed that electric field is acting in one direction, whereas the magnetic field is acting in the exact opposite direction. So if this was the assumption we started with, we said the electric field will act along the y-axis, magnetic field, let's assume it to be acting along the z-axis, and then the particle is traveling with a velocity v in the x-axis. So the force due to the electric field felt by the particle is in the direction of y-axis, and the force being felt due to the magnetic field is also along the y-axis but in the opposite direction. Now you might also check out with the Fleming's left hand rule whether this is true. So if electric field is going upwards, obviously the force being felt will be in this direction. If I assume the particle to be, let's say, either electron or proton, if you are taking a proton, then it will act, since the electric field is from the positive charge towards the negative charge, obviously the proton will be attracted towards the top. Now if it's also a proton and there's a magnetic field in this direction, I use my Fleming's left hand thumb rule. So remember, the middle finger indicates the direction of the charged particle. So I point it, I keep it along the direction of V, and my index finger is along the magnetic field. So I need to turn it so that the magnetic field, remember, is coming out of the blackboard. It's coming out of the blackboard, so I'm holding it this way. Then the thumb will show me the direction in which the force is being felt. So it's showing downwards. So FB acts along the y-axis but in a direction opposite to that of the force being felt by the electric field. So that itself shows that these two forces act in opposite directions when the configuration is thus. Now suppose there's an interesting thing over here. We said force due to electric field is Q into E, ignoring the vector directions, and FB is equal to VB into Q. Now suppose we already discussed FE and FB to be acting in opposite directions. Suppose I make FE to be equal to FB. Then what will happen to the particle that's moving with velocity v in the x-axis direction? It will move without getting deflected. It will move without getting deflected. right? So which means I can equate the right hand sides. QE equals QVB. So Q and Q get cancelled. I keep V on one side and I get E by B. Now this is an important conclusion to train our sights on, because what it tells you is that when the electric field intensity and the magnetic field intensity, when the ratio of these two is taken, right, that should equal the velocity of the particle. And what is this velocity? This is the velocity at which the particle is traveling. And at this velocity, the particle will travel undeflected, which means it will neither move upwards or downwards, nor execute any circular motion. Rather, it will continue moving as though there were neither the presence of the electric field or the magnetic field. So what significance does this hold? Imagine that a particle is traveling in a straight line with a certain velocity. Now I switch on the electric field. Obviously the particle starts getting deflected in the direction of the electric field. Suppose I am getting a proton to move here and I switch on the electric field which is going upwards. Obviously the proton will start getting deflected upwards. If it's an electron, it starts getting deflected downwards, right? Now suppose I also switch on the magnetic field and I switch off the electric field, I switch on the magnetic field. Then under the influence of the magnetic field, we saw that the same particle will now start executing helical motion, right? Now suppose I switch on both of them, then the motion that will be executed will be a combination of deflection and helical motion in the direction of deflection. Now when is it that a particle will travel straight without exhibiting either a deflection or a helical motion? It is when B is equal to E. When the ratio of E and B is equal to the velocity of the particle, then the particle will continue to travel in a straight line. So in one sense, this equation is what scientists call the velocity selector. The velocity selector. Why is it called a velocity selector? The reason being, let's assume there are a bunch of particles that I have with me which are traveling in different velocities, and I want to separate out certain particle of certain mass or of a certain charge. How do I do that? I find out at what velocity it's traveling and I adjust my electric field intensity and magnetic field intensity such that the ratio equals the velocity of that particular particle which I want to separate out. So what happens immediately is that particle starts traveling undisturbed in the same straight line, whereas all other particles tend to execute a combination of deflection and helical motion. Whereas that particular particle whose velocity matches the ratio of E by B continues undeflected or undisturbed along the straight path. That's why this ratio is sometimes called the velocity selector. Now why is it so significant? The reason it's so significant is that it allows physicists to separate out particles of a certain nature. It was the same way that mass spectrometers work. Mass spectrometers are special instruments that help physicists separate out certain charged ions from the rest. So mass spectrometers work on the same principle. The same principle was also used by J.J. Thomson in 1897 to find the charge to mass ratio of an electron, the E by m ratio of an electron.